My name is Jess. I'm a researcher at Lund University in Sweden, where I work on people and pollinators in agricultural landscapes. My PhD was in crop pollination, so I worked on pollinators and pollination ecology, particularly in squash production systems. And it was this experience working with farmers as well as the pollinators that brought me to Sweden to work on the PoshBee project at Lund University. So PoshBee was a project that was funded by Horizon Europe, and it was in response to a call by the Commission to better understand drivers of pollinator decline. So PoshBee aimed to understand how multiple stressors, particularly nutrition, pesticides and pathogens, affected pollinator populations and pollination services. And it did this across European countries, working with 3 model species. So they had the honeybee, the bumblebee, Bombus terrestris, and the solitary bee, Osmia bicornis. It worked in lab and field settings with a range of stakeholders, so from policymakers right through to beekeepers and farmers. So pollinators are critical within ecosystems. They support biodiversity. Some 80% of our crop and wild plant species depend on pollination for their plant communities to exist, and that in turn supports healthy, intact food webs. Our crop pollination services are also super important for food security, and that food security contributes some of our most nutritionally important and economically important crop species that we have. And that is estimated to be worth 15 billion euros to our economy. Pollinators are also responsible for providing other services and uses that we may not even think about. So, for example, they contribute to medicines, fibres, but also the maintenance of green space and other important heritage features that we have in our landscape, like meadows, which we know are really important for our health and well-being. And we also know that initiatives to support pollinators can provide us with multiple benefits. So, for example, reducing pesticide use can be really beneficial to pollinator populations, but it can also improve air quality, water quality, and also ensure that we have cleaner food. Have been declines in arthropod populations, including pollinators, and those declines have been widespread. There's evidence of declines in data sets across the globe. What is particularly concerning, or what we're now finding, is that those insect species that used to be very common are declining at a faster rate than other species. And that may explain why people are starting to take note of insect declines, because it's those species that we usually see all around us that seem to be the ones declining. And that is particularly worrying when we think about pollination services, because those common or abundant species tend to provide an almost disproportionate role in pollination services, particularly crop pollination services. So it's highly likely that their declines have already started to affect how our ecosystems are functioning. And things will continue on this way all the time that we have a continued population growth and continued demands for resources in a finite planet. But it doesn't have to be this way. We know that human mediated activities are responsible for a large proportion of these declines, even if we can't be certain exactly what ones. And that implies we can do something about it. So, for example, we know many insect species thrived under less intensive agricultural production. They really like semi-natural grasslands. And we're able to restore those landscapes. We now have the opportunity under the Nature Restoration Regulation to do something about that across Europe. And I think that could be a really positive step towards restoring or mitigating these declines of insect species. Use is a serious driver of pollinator decline. It's created contaminated landscapes that expose our pollinators to a mosaic of complicated pesticide exposure. And this real-life exposure, coupled with the other stresses that we know pollinators encounter, is completely disconnected for how we know pesticides are regulated. So this means that pesticides enter the landscape really with no prior understanding of how they will work in interaction with each other, but also the landscape itself. But habitat loss is the most severe stressor overall. So habitat loss, we're talking about changes in land use, land cover and configuration, because all species, humans included, fundamentally need a place to eat, sleep and reproduce. So without this, without suitable habitat, there's really nothing to support these populations at all. And often, of course, these interactions or these stressors can interact. And we know that that's the case with agricultural intensification, where we've lost or degraded our habitats for pollinators and combined that with pesticides, as well as other stresses such as pathogens and also climate change as well. So the PoshBee project put bee species that I mentioned earlier, the honeybee, solitary bee and bumblebee, into 128 different landscapes across 8 countries. Those landscapes were focused on oilseed rape fields or apple orchards. And at the end of the season, we quantified the pesticides that were found within the pollen stores for each of those bee species. My study focused on the pollen stores of Bombus terrestris, the bumblebee species. And we relate in our study the pesticides that we find in those pollen stores to how well they grow, survive, and reproduce. We know that pollinators are exposed to multiple pesticides as they go about their daily lives, collecting food, nesting, and reproducing. And the extent to which this happens varies across the pollinator community as the different lifestyles affect, for example, how much food they need and where they choose to nest. And this means that pesticide exposure can affect species in different ways, depending on their lifestyles. So it's therefore important to think about those lifestyles when you're doing these kind of studies. So for example, you have a honeybee, which has a really huge colony. It forages over large areas of the landscape, right through to the solitary bee, the Osmia bicornis, which is much more restricted in its foraging range and it lives alone. We focused on the bumblebee, Bombus terrestris, because its lifestyle is somewhere in the middle of these 2 species. And this means that it's relatively representative, or I should say more representative of the broader pollinator community than if we were to focus on the honeybee, which is what risk assessment predominantly focuses on today. So we found that colonies were exposed to multiple pesticides. On average, there was 8 pesticides found within each colony and up to 27 pesticide compounds in one. We also found pesticides in pollen stores that had been known to be restricted prior to the study. So for example, we found imidacloprid in 8% of our samples across Europe a year after the pesticide had been restricted. But the number of pesticides tells you nothing about how risky or the likelihood that those pesticides have to cause harm. For that, you need to take into account the amount of that pesticide as well as its toxicity, so how poisonous that pesticide is. And so we do that for every single pesticide that we find within a bumblebee colony. So we take the amount of the pesticide and we weight it by its toxicity to combine those 2 values, and then we add them all together. And this produces something that we call pesticide risk that we relate to bumblebee colony metrics later on. Our results show, perhaps unsurprisingly, that bumblebee colonies do not grow as well. They're smaller and they produce fewer offspring when pesticide risk is high. In other words, pesticides stunt bumblebee growth. But what I think is particularly interesting is the landscape context. We see that bumblebee colonies grow better when there is more semi-natural habitat surrounding these crop fields and there's less cropland. And they don't grow as well, conversely, when there's higher amounts of cropland in the landscape and less semi-natural habitats. This highlights the importance of semi-natural habitats in supporting pollinator populations and also even potentially mitigating or buffering pesticide effects. And these findings aren't just shown in our study, they're also echoed in others as well. And this aligns with the European Commission's broader ambitions, not only to reduce pesticide use and risk, but also to restore semi-natural habitats. Our study demonstrates that despite one of the most rigorous pesticide risk assessments in the world, we're still failing within Europe to protect non-target species from pesticide use. Our study focused on bumblebees, a species which is known to be relatively resilient to pesticides because it has these social colonies which are thought to buffer pesticide effects. And this means that the effects that we observed are actually likely to be more severe to the rest of the pollinator community. Since these non-target organisms are essential for maintaining ecosystem services like soil health, pollination, and natural pest control, improved pesticide regulation could actually enhance the agricultural resilience of our systems. Our study focused on flowering crops, but of course most pesticide use occurs on non-flowering crops. It's across all sorts of crops in the landscape. So moving forward, it would be interesting to assess those risks to non-target species as well. So a similar type of design, focusing on other non-target organisms in different cropping systems, also replicated across Europe. Monitoring pesticides after they've been approved, like we did in our study, is essential for safeguarding biodiversity from unexpected effects from pesticides when they're used at scale. But this type of post-approval monitoring must feed into the regulatory process so that we can continually reevaluate farmers' pesticide use and make adaptations where necessary. Our pesticide risk metric is particularly useful here because it can help us target landscapes that could be high risk for monitoring purposes. And our pesticide risk metric is also pragmatic because it deals with a huge amount of existing toxicity data that we already have established protocols for and a huge wealth of information. It also deals with the multiple pesticides that we know pollinators encounter, albeit in a relatively simplistic way. Finally, we know from other work that pesticide risk is predictive across bee species. So we could, for example, use one bee species, like Bombus terrestris, as an indicator of risk or fall risk for other bee species. So it's incredibly challenging to assess the risks from multiple pesticides when you consider just how many there are out there in the landscape and the possible combinations of these that could occur. We do this in our study in two ways. Firstly, we used a post-approval monitoring type approach. So we're working in real landscapes that capture these multiple pesticides that bees are exposed to, and we integrate this information using a concentration addition approach. Now, this is a relatively simple approach that could be underestimating mixture effects, but it's generally considered an excellent starting point if you don't have additional information about mixture toxicity. So our work and that of others lays the foundation for improved pollinator protection in Europe. It's time to consolidate and centralize our scientific understanding so that we can step towards a more systems-based risk assessment for pollinators. This doesn't mean that the regulatory process should become tighter or more complicated, rather that it should become more realistic and robust. If you're interested in learning more about the PoshBee project, they have an excellent website, poshbee.eu. There, they summarize the project, its aims and objectives, but they also contain in their media center instructional and educational videos, policy briefs, and stakeholder summaries, posters that summarize some of the great work that's been done in the PoshBee project, not only on pesticides, but also on those other stressors too. My key message is that pesticides can be sustainably reduced, but this needs us to reconcile the seemingly conflicting goals of agricultural production and biodiversity protection. We all share a common goal that fundamentally centers around the need for healthy ecosystems. It's time for us to work together to achieve it.